Hello everyone, my name is Jinshu Wu and I'm a technical specialist at Altair. Today I'm going to walk you through how to use HyperMesh CFD to create surface mesh for ultrafluidX, fan performance, and noise simulations. Here is the workflow for this meshing process. First, we import and sort CAD parts. Then we create initial surface mesh for all solid parts. In the next step, we will review all mesh that's been generated and check if the part has a high number of elements and it is not flow critical, or if the part has large internal volume that's not the interest of this flow simulation. If neither case is true, then we can export the surface mesh to STL files directly. If one of these scenarios is true, then we will wrap the mesh first and then export the mesh. So first, let's launch the HyperMesh CFD from the Start menu, and you will see the icon like this. It will pop up this starting dialog from the Start menu. Select Aerodynamics for your UltraFluidX. Select Geometry Meshing for the surface meshing. We will have additional videos for the following steps like case setup, post-processing, and design exploration. And then select your working directory. This could be the directory that you save your project or the directory that you have the CAD files. Then click Create Session. Okay. As the first step in the meshing workflow, we import the CAD file into the HyperMesh CFD. So go to File, Import, Geometry Files. Select the appropriate CAD file and then click Open. In the Open dialog, make sure in the Topology section, in the target units, select MKS, which stands for meter, kilogram, Newton, seconds. Basically, uFX is only use this unit system. And then click Import. So HyperMesh CFD will import the CAD file. Once the import is complete, it will display the imported CAD file. You can drag your mouse around. The left key is the selection. Middle wheel is used to zoom in, zoom out, and then if you press the middle wheel, it will rotate the part. You can also use the right key to move this around. Another way to rotate or manipulate the model is to use this little cube on the lower left of the GUI, and you can select different views to view the details of this CAD model. Also on the left of this panel, you can see your part browser, which basically listed all the parts in this CAD model. In order to keep both CAD and mesh in this HyperMesh CFD session, we need to convert the current model to mixed. So in the Home section, click Convert. And then basically this will display the dimension of your current CAD model, and then click Convert. Now, once the conversion finishes, it will show the current model in gray as mixed. Then right-click in any empty space and click the green check mark to confirm this operation. This is a very standard operation in both HyperMesh CFD and HyperMesh. So we will keep using this process to finish and confirm any operations. Then we can start the workflow with the critical flow parts. In this example, it's basically the fan and shroud. Both parts need high-resolution elements in order to describe the curved solid parts accurately and capture the flow around them accurately. Since UltraFluidX post-processing are using surface element to show surface results like pressure and wall shear stress, we also need more uniform mesh for those parts. So first we isolate the fan and shroud. You can do this in one of two ways. So you can do this in the part browser, hide all parts, and then search for the part that you're looking for. In this case is the shroud and the fan. So this will just display the shroud and the fan in the screen, and then you can go around and check the CAD model. Another way to do this is in the GUI. Select individual parts, for example the canopy, and then right click and click hide, or just press H. And then until you have a clear selection of the part that you are looking for, in this case is the shroud and the fan. You can press Ctrl to multi-select parts, and then once you have the selection finished, right click and then click isolate, or just press letter I on the keyboard. So this will isolate the fan and shroud. Next, we will go to the Mesh tab and then go to the Mesh section, click Surface. So this will create initial surface mesh. Change the meshing method to rigid body, and then set the average element size to 5 mm. So again, since this is in the MKS unit system, it is 0.005. And then set the minimum size factor to 0.02, which means the smallest element is 0.1 mm. Also set the geometry feature angle to 2 degrees and the maximum deviation factor to 0.02. Again, 0.1 mm maximum deviation factor. Then select both fan and the shroud, and the GUI will highlight the bounding box size of this combination of your selection, and then click Mesh. So this will start the meshing process. It will take a couple of minutes to finish, and the progress bar is located on the lower left corner to highlight the meshing process. Once the surface mesh is finished, you can right-click on the empty space and click the green check mark to confirm and finish this operation. And then we can zoom in and look at the finished meshing, and this mesh looks pretty good. Again, the meshing criteria is trying to capture the feature of the geometry, and in this case it will represent the geometry very well. And then we can mesh the rest of the part of the machine. One way to quickly isolate or show the rest of the part is to right-click on the empty space and click Reverse Displayed, or just press R. This will hide the part that we just finished and show only the rest of the machine. So in the displayed parts here, there's no fan and there's no shroud. Then what we can do is basically repeat the previous process, but use a lower resolution. So again, in the Mesh tab, go to Mesh section, and then click Surface. But this time, use a coarse mesh, so the average element size set to 5 cm or 0.05. Still keep the minimum size factor to 0.02, which basically the smallest element is 1 mm. And then also set geometry feature angle to 15. Keep the maximum deviation factor at 0.02, so the maximum deviation is also at 1 mm in this case. Then select all the surface that you plan to mesh, and then just click Mesh. Again, the progress bar on the lower left will show the meshing progress. And then once the meshing is finished, you can zoom in. You can also right click on the empty space, click the check mark to confirm the operation, and review the meshing quality. And the initial quality of this meshing looks pretty decent. So once we finish the initial surface mesh, we can check if we have any surface meshing issues. We are mainly looking for 3 issues in UltraFluidX simulations, and they are duplicates, non-manifold, and free edges. These issues will impact simulation cost and accuracy. So to check if the surface mesh has this issue, go to Discrete tab, and then in the Quality section, click Repair. And then the tool will automatically search the displayed mesh, and then search for all the issues, possible issues. The default option is show the duplicates, and in this case, there's 0 duplicates. User can change the search option to non-manifold. In this case, also shows as 0, and then also check free edges, as I mentioned. These 3 are the critical criteria for uFX simulation. If everything looks good, then right-click and click the check mark to finish the mesh quality check. In some situations, we will need to wrap the mesh, as I mentioned at the beginning of this tutorial. If the part has very large internal volume that is not part of the interest of this flow simulation, or if the part has large number of elements and it is not a flow critical part, then we prefer to wrap the mesh. Another common reason for wrapping is when we have issues, in case that we have some meshing quality issues, such as duplicates, non-manifold, and free edges. Sometimes it's hard to fix them, even using the auto repair tools to fix all of them. So to avoid this time-consuming process, we can also just wrap the mesh, and in most scenarios, this will provide a mesh that meets the uFX simulation requirements. So to start the wrapping, first we need to isolate the part that needs to be wrapped. So in this example, we will just wrap the engine. So I will select the engine and then click Isolate on the part browser. So initially, we can use the section cut tool in the lower graphic GUI. Click this section cut and then click plus sign, create a new section cut. And as shown here, you can see that there are a lot of internal volumes, pretty large internal volumes that is not our interest of this underhood thermal fan cooling airflow simulation or fan noise simulation. So we don't really care about what's going on inside this large volume. That's the reason we want to do the wrapping. And then we can also turn off this section cut by uncheck this section cut. So first we will isolate the part that we plan to wrap. Normally I will try to avoid wrapping a thin panels like this heat shield, so I will leave this out. Also for this belt, for the similar reason, I'm also going to hide it and to exclude this part from the wrapping. Next, we will need to fill all small holes and gaps that may result in wrapping inside the volume. For example, there are some open holes that we know it will lead into the interior of this engine, which may result the wrapping process get inside the volume, which will keep that volume inside the model. So that's something that we try to avoid. So in order to make sure that all the small holes and openings are being closed, in this case, before the wrap, so we will fill those holes first. So what we do is, again, go to in the Discrete tab, and then in the Edit section, click Cap, and then select Cap Holes, and then change the selection filter to Parts. That's normally more reliable. And then change the maximum width to 0.2 for this specific case. And then select all the parts that you plan to wrap, and then click Cap. Again, on the lower left side, it will show the progress of this cap filling process. So once it's finished, again, you can right-click empty side and then click the check mark to finish this operation. Don't worry about the fill cap element quality. Once we start the wrapping, it will fix all these issues in the next step. So next, we will just wrap this engine. So in the Discrete, again in the Discrete tab, Edit section, click Wrap, and then click CAD Wrap. So here for this specific model, we will set the split large element size to 0.05, which is basically 5 centimeter, we will set the stitching tolerance to 0.0001, which is 0.1 millimeter. We will also set the resolve overlaps tolerance to 0.0001, again, which is also 0.1 millimeter. The maximum allowed gap in this case, we will set it up at 0.01, which is 1 centimeter. And also we will uncheck the quality cleanups for this case. Once you finish the setup for the CAD wrap, you can select all the parts. Again, it will highlight the bounding box size for these wrapped parts, and then click Run. And again, on the lower left corner, you will see the progress of this wrapping process. Once the wrapping process is finished, it will display wrap mesh end at the lower left progress bar location. So then what you need to do is right click in the empty space and then click the green check mark to finish the wrap and confirm this operation. You can zoom in and look at the wrapping quality. Again, this is pretty good. It maintained all the feature lines and the details of the geometry. Okay. And then we can also go back to the section cut. So go to the section cut and then turn back on that section cut. Now you can see all those previously showed internal volume are disappeared. So basically what we have here, it is a one closed shell. Okay. So again, for different cases, you may have very different type of geometry. User can adjust the split large element size and also change the resolve overlaps tolerance and also change the maximum allowed gap to change the meshing size and the quality. Just keep in mind that the maximum allowed gap can be reduced to describe more details in the mesh, but keep it greater than 1/5 of the maximum element size in order to have a quality mesh, especially for thin panels. Okay. So once you finished wrapping, the last step for this process is to check the mesh quality. Again, similarly to the initial mesh that we did. So for this wrapped mesh, again, go to Discrete tab. In the Quality section, click Repair. And similarly, we will go through to check for duplicates, non-manifolds, and 3 edges. So in this case, we are clear of those 3. So right click and click check. The final check for all the mesh parts is, before we export the mesh, is to check the element normal directions. So what we can do is to change the model color selection in the lower portion of the graphic GUI. Change this to surface normals. And in external airflow cases or aeroacoustic cases, it should all show as red, as the normal positive towards outside, and this is required by UltraFluidX. If there is any issues, so you can also check the details or small places around this part. And then you can also turn on the section cut. Again, the internal surface in this case will be shown as blue. Again, this is what it will show as a one closed shell wrapped mesh. And then, so that's the wrapping process. And once you're finished, to save this session, you can go to File, and then Save or Save As. And then save the file to a HMCFD file, and then click Save. I would recommend you to save the session into a different session files before any major steps, like initial meshing or wrapping, especially when you have a large model or very complicated model, to avoid loss of data. So once all this finished, we can export the SurfaceMesh to STL file. So in the File menu, select Export. Then select the solver deck. And you can select the file type as STL. And then you can type in the file name. Then click Save. This will bring up the Export STL dialog. There are different ways of exporting the part. You can export all the mesh in this session, which basically it's the full machine at once, or you can export only the displayed model. So in this case, it's just the wrapped mesh. And then click Export. So this will export the surface mesh of this wrapped engine to a STL file. If user wants to go directly to the next step of the case setup for uFX, you can click the data transfer in the Home section, and then you can select all the part that you plan to move to the next step. You can, in this case, you can turn on the whole model, and then just select the whole thing, and then click Transfer. So in this case, HMCFD will convert all the mesh that you have in the previous surface meshing step, and then transfer it to this case setup GUI where you can set up your simulation. So this is a quick start guide on how to use HyperMesh CFD to prepare SurfaceMesh for UltraFluidX fan simulations. HyperMesh CFD is built on top of our HyperMesh software, and it has many powerful tools that has already been built in, as you can see here in the edit section or in the geometry in the discrete sections. So I strongly recommend users to test and try different ways to optimize your specific scenarios and your own workflow. So we value and we welcome any feedback, and thanks, and have a great day.